Jeremy, Borden, Christian.
Hello.
How was the exam? Any comments?
I thought it was good.
Okay. Reasonable? Okay. So I had a question for you guys before I begin. So we have what, 4 of us here. So 2 of us are not here. So Travis and Matt is not here, but I think you guys are attending this regularly. I think Matt and Travis probably depend on the recording. So the question for you guys is it, would it be okay if I take extra 5 or 10 minutes after the class, after each lecture? Are you guys having a class immediately after this?
This one's my last one, so that's fine with me.
Yeah, I should be free for extra few minutes.
Extra few minutes means can it go all the way to 10 minutes?
Yeah, it should be good.
Okay, great. Because that would really help me to cover things. I've noticed that instead of postponing it to next class, if I just continue and finish it off, it is a lot more economical. Next time I come back and remind you guys of everything, it usually takes double the time. So if I can do that, that will be good. I do know that Borden, you said that on Friday you're not available, correct?
I mean, I guess I can. I'll go over a little bit, but like once 3 o'clock hits, I have a meeting, so I'm gonna like join that. I'll just
Sure.
watch the recordings.
No, I think even 2 days a week would really help. So on Friday, if at all I do it, I'll do it for a few minutes rather than 10 minutes. Yeah. So let's see how it goes. At least I've done this for, or it was not my idea. Students suggested this in my graduate class, and it has come out really good because they had this class on Tuesday and Thursdays. They have their classes. And remember, during snow, we lost 2 of the class, 1 week of classes there. And it was easily made up using this manner, like just 10 or 10 minutes or so. So we'll see how it goes here. If you allow me, at least I can try. Okay, so thanks for that. So I don't know whether I'll use it today or not. It typically depends on whether I'm finishing on time or not. So I may not use it all the time. Okay. So I haven't graded midterm 3 yet, but I'll do that soon. We will have a homework 8, which is not posted yet, but I intend to post it almost today itself. And this will be due Monday. And yeah. There will also be a notes related to what we are doing, since I'll be doing a lot of things around here. And in this form, it is not available. I should say it's available at a lot of places. It helps to have the notations around in one place. So I'll give you some notes. It'll be in the form of a homework, but it won't be due. So you'll see that show up. So I'll tell you more details next time. Okay, so let's proceed with what we were doing, special relativity. More specifically, we did Lorentz transformation. And Lorentz transformation reads as so that is x prime, we keep it the same. Y prime, we will keep it the same. That means to say we are talking about a relative velocity. If there are two frames, two people moving with respect to each other along the same line, then how do they observe things? So you're saying they are moving in the z direction, so the z prime and ct prime gets coupled in a sense between the two observers, and it's given in terms of beta gamma. Where beta is a measure of velocity relative to c, so it's a dimensionless parameter, and it is always less than or equal to 1, and gamma is equal to 1 over 1 minus beta squared, and is always greater than or equal to 1. That's how we quantify this transformation for each observer who is moving with velocity v relative to another velocity. So that is such a transformation. So due to that reason, it is meaningless to compare time between two observers which are moving relative to each other, for that matter, even position. Like they won't agree with their position. They will be, in fact, coupled in complicated ways. But a quantity that they can compare is, we found out, is the following. So that minus c t prime squared, that's a c squared t prime squared plus z prime squared, is always the same as minus c squared t squared plus c squared. Now that's called an invariant length, exactly like in rotations. The radius of the circle will not change if the center of the circle is at the origin, is on the axis, if you want. So every observer between every rotated observer will measure the same radius, and it's so this quantity is something like a radius, but not a normal three-dimensional space radius. This has a negative sign in it, and in that sense, it's called a Minkowski space, and this is an invariant distance in the Minkowski space. It's good to introduce some notations here, and I showed that in the midterm also, so that notation was introduced there. So let's say when you have these coordinates, this could be a position or any other physical quantity. Let's say we have P alpha. Let me write first space. I want to talk in terms of position itself. So let's we are going to define what is called a 4 vector. And 4 vector here is x alpha. And like we say, x, y, z are the components of a vector. Here, this would mean c times t, and x1, x2, and x3. This could be x, this could be y, this could be z in general terminology. So I just call them x1, x2, x3. Often this is additionally called x0. Oh, sorry, I should make it upstairs. I'm sorry. So this is 1, 2, 3, and this is x0. Maybe write it again. So this will be, these are combination of 4 components of a vector. So x0, x1, x2, and x3. And by definition, this would be c times t, so that it has the dimensions of time. So the 0th component of this vector is time scaled with speed of light. And this is your x, this is your y, that's your z. So we would like to define. That's a 4 vector. Not only that, we will call this a contravariant vector. The name is not really important. It just means that the index is in the superscript instead of the subscript. That's what it exactly like that. We will also define what is a lower script 4 vector. For the same position vector, we have 2 ways of describing them. One is with a superscript index and one is with a subscript index. And this one would be pretty much the same as the other. So let's say this is x0, but here I'm just writing the components, but I don't tell you what exactly these components are. And these components will be minus ct this time, x, y, z. So the same coordinates, but you switch the sign of t, and this will be called a covariant 4 vector. Since we are talking about time and position, this will very soon be called a 4 position vector. It's the special vector, so that's a 4 position vector. That's nice. What do we do with this? The quantity we'll be mostly interested in is what will be called x alpha. X alpha. And remember your index notation long back, which we have been using consistently. These are 2 indices that has been summed up. And in this way of doing it, it will always come one upstairs and one downstairs. Earlier we were doing indices, we didn't really bother too much about which was upstairs and which was downstairs, which was subscript and which was superscript. Here it matters, and this will be by definition, by the notation if you want, it's x0, x0 plus x1, x1 plus x2, x2 plus x3, x3. Right, I replaced alpha with 1, alpha with 2, alpha with 3, and then alpha with 0. So there are 4 terms in it. So it is a summation of alpha going from 0 to 3. Which, if I were to now use the identification of it with time, this is seen as minus c square, t square plus x square plus y square plus z square. And that's your invariant length. But we know that this doesn't change there. if I were to change my coordinates, this will, so what I've learned here is that x alpha is the same as x prime alpha in Lorentz transformation. So this remains the same. That's equal to a constant. So instead of saying this construction remains the same, we will write x alpha, x superscript alpha, x subscript alpha is equal to a constant under Lorentz transformation. Okay, any questions there, notations? Okay. We'll be typically interested in differential statements. So let's write the differential statement associated with this. So x alpha, we said, is x0, x1, x2, x3, and of course the covariant part of that, which is the same as ct, x, y, z. If I have two such position vectors very infinitely close to each other, I would say the difference between those two vectors will be defined to be dx alpha, right? That's a small, tiny, infinitely tiny vector of infinitesimal magnitude. This will be equal to, again, dx0, dx1, x2, x3. That's equal to c dt, dx, dy, dz. So we are building the calculus on this space in the standard way that we typically do. But now, notice if I were to make a small displacement in time and small displacement in x, it will be different in different frames. But what is more interesting is, or what remains absolute, if you want, between different observers is this product of this infinitesimal incremental four vectors, and this will be equal to, as we saw, minus c square dt square plus dx square plus dy square plus dz square. Let me call that, since we'll be invoking this again and again, let's define this to be ds square. So again, S has this idea of this invariant distance. So again, the point would be, now remember, so what is the theme here? So this is like think of Newtonian physics. What do you do when you first time encounter Newtonian physics? First you define time, right? And typically it's not the time, it's in typically dt, right? You're interested in change in time. You can also say it is a finite extent of time. So you define what is change in time. You say time has to be a monotonic function. You cannot keep jumping around from future to the past. So time is a monotonic function. And then you define displacement. It's a three-dimensional space. So we have three components to the displacement. And then we define velocity. So these two we typically don't define, right? It's an intuitive understanding that time is a monotonic function, displacement is difference between two positions, but velocity in terms of that is well defined. Like it's a derivative or change in position over change in time in the limit time tends to zero. That's a well-defined concept. And acceleration is change in velocity over time. That's what you do. And then again, these two are definitions. Those two are, in a sense, assumed to be having an understanding that we intuitively get. And now again, we say there exists something called mass, there is something called force. We don't precisely define them. Force is like when you push something, whatever the intuition you have for that, that's force. Mass is something that occupies space. We never precisely define it. But Newton came and informed us that mass times acceleration of any mass for that matter is equal to the vector sum of these forces, which is very powerful equation. It seems it has been valid all through, except when things started going very fast, there have been issues, and that's we are trying to rectify. If you want, what should we change to accommodate for this new understanding we have about relativity? And the point here is that when we define velocity, we have been defining it with time, and that is okay. Velocity will not change. We will not change the definition of velocity, but we would like to ask what are the quantities that that can be compared between two observers if velocity is not the candidate in them. So that's the theme here. We are trying to match or trying to get what is the other quantity. And the key will be that instead of doing calculus with dt, we will do the calculus with ds. Instead of defining derivative with time, we will do the derivative with respect to invariant distances. And that will let us define velocity, acceleration, force. All of them will have four forces. There will be a four velocity, there will be a four acceleration, there will be a four force, there will be a four momentum, and so on. So that's what we want to build. And in that context, let's write this equation again, the invariant distance equation. Let's say ds square is equal to minus c square dt square. And then we take this common out. So that's 1 plus dx by dt square, where if dx was the difference in the position of the particle, then that becomes velocity, right? So that's, but actually I took out a c also, the 1 over c square. And that is dy by dt square 1 over c square plus 1 over c square dz by dt square. But that's can be processed a little. This is nothing but minus c square dt square. And oh, what's the mistake? The mistake here, right? Algebraic mistake, trivial mistake. When I went from here to there.
Negative signs, right?
Yeah, negative sign, right? So this is negative, that's negative, that's negative. Thank you. So that makes this 1 minus, that's velocity square, right? So that's vx square plus vy square plus vz square, that's velocity square. That's beta dotted with beta, which is nothing but beta square. Beta square is beta dotted with beta. Velocity dotted with velocity is velocity square. And 1 minus beta square is gamma square. That's minus c square dt square 1 minus beta square. And divide, if you remember, gamma is equal to 1 over 1 minus beta square, square root of that. So square of that will be gamma. So it seems like there is a connection in here that we can say minus sign. So it's dt square, gamma square, and s square minus. So we will have a relation here that the S is equal to C dt times gamma. So the idea is that whenever we are interested in a derivative with respect to time, where derivative is always defined as a ratio of a small infinitesimal time element, we will switch it over to an invariant distance by multiplying a Lorentz factor of gamma. So that will be very handy. So keep this here. We won't use it immediately today, but we will use that in the next class a lot. Okay. Okay, so before I proceed further into velocity and so on, I think I should derive a few standard things so that I can use them if necessary. And one of the thing is length contraction. Right? So what do we mean by? Let's begin by time dilation. So this is time dilation. So we have already seen that coordinates, position and time is transformed whenever you have a relative velocity between them. So the difference in position will also change, right? So we write that here. So let me start from here and go back. So z, yeah, z1 prime is equal to gamma times z1 minus or plus beta gamma times t1, c times t1, and c times t1 prime is equal to, so that's beta times gamma times z1 plus gamma times ct1. Similarly, I can have z2. This will be z2 prime is equal to gamma times z1, z2, sorry, plus beta gamma times c2, and c2 prime is equal to beta gamma z2 plus gamma times c2. That means what we're talking about is that in this space there is a point z1, ct1, and there is another point z2, ct2, as seen by one observer. But this will be same as delta z and c times delta t, where z is equal to z2 minus z1, and delta t is equal to t2 minus t. So basically we are saying we want to talk about difference in two coordinates rather than the coordinate itself. Or whenever we say the coordinates itself, it is understood that there is an origin there. So this is origin independent. So when you subtract them out, that's also valid. So in Lorentz transformation, since it's a linear transformation, it allows, it's the same transformation when you talk in terms of difference in coordinates. That's equal to gamma times beta gamma and beta gamma. So that's the statement. I put that in detail there. But now that I concluded that, I don't need this. Again, there are 2 points. Delta z is the difference between two coordinates. Now, we want to talk about a particular kind of measurement, and that is involving a watch. Right? So z is, let's say, or delta z, let's say t. Okay, that's it. Z is position of a watch, right? So that is a watch, and Z prime is position of another watch. And if Z prime is the position of another watch, the other watch is moving with respect to the first watch, correct? Now, if this is in the rest frame, the position of a watch in its frame, that's a special thing I put in. Oh, am I going outside that? Oh, it's. Come on. So what will be the change in position so let's say this is the rest frame. So let's say you're wearing a watch and you ask what is the change in the position of, at 2 times you measure the position of the watch with respect to you. What is the difference in the position? It will be 0. If you're at rest with respect to the watch, it will be 0. So in the rest frame of any quantity, that will be equal to 0. This distance is 0. Only for the watch, not for any other kind of measurement. For the particular measurement of the watch, that will be equal to 0. And then you can say if that is equal to 0, there is a condition here, right? So delta C times, so now let me calculate C times delta T prime is equal to this times delta C, that's 0. So that's gamma times C times delta T. So again, remember what is going on. So if this is the rest frame, this is the time measured in the rest frame of watch. Right. And this is another observer who is moving, measures the same. So there were two instances. There was a time measured in by that observer, and this is that time measured. And remember, time is relative, right? It doesn't have to be the same. We convinced ourselves of that. Sure, that in a moving frame, when we say moving frame with respect to that rest frame. So once we decide on a rest frame, and it's with respect to that. If you change your rest frame, things change. Things conclusions change. It's again, remember, time need not be compared at all. It's not a good thing. But if you were to compare, this is how things will look like. C cancels out, and we have delta T prime is equal to gamma times delta T. Gamma is always greater than 1. So delta T prime is always greater than or equal to delta T. Oops. Okay. And that's called time dilation. But that's it. I mean, time doesn't have to be the same. We agreed upon that. Time is relative. So once we accept that, there is nothing meaningful in there because we cannot compare them. Whenever we are comparing, we should be comparing something invariant. But that's the idea of time dilation. Same thing we can do with length also, right? So we can, we are again construct two events where how would you define your length? So that's it. So here we had to say, right, there is a rest frame, as a watch sitting. So you create a story and you have to measure two events, right? And then we say, how does the two events look like between for different objects? So similarly, let's say, what does it mean to say length, right? How do we measure length of a rod, let's say? So we have come up with a way of measuring length. So this is broadly called length contraction. So again, we have delta z prime. So there are two frames. So we just have to recognize what is each of these quantities is. And there is delta z, and there is c times delta t. And we have a rod which could be moving. So that is an actual rod. And there are a lot of frames, right? There is one frame which is fixed to the rod while it is moving. And there are a lot of rods, a lot of frames which are actually moving with respect to this rod. Now, if I were to measure the length of the rod, I would say, okay, so how do I measure things? If I'm in the moving frame, I have to be careful where I am. Right? So I have to be, but if I'm in the length, if I'm in the rest frame, I don't care, I move around. Like I first, if I'm in this rod, if I'm measuring the length of this rod and I'm in the frame of the rod itself, I measure it at today, and then later on I measure it at time t2 there. So that's a freedom I'm going to say I have, because I have to define how do I measure my length itself. So in the rest frame, I would say that delta t doesn't have to be 0. So in the rest frame, so this is the way I'm defining. In rest frame, delta t need not be 0, need not. But in the moving frame, the requirement will be that if you measure the length, you have to measure it at the same time. Remember, simultaneity doesn't have much meaning in relativity, right? In one frame, if it is simultaneous, in another frame, it's not simultaneous. But with that feature of not having that absolute concept, in a moving frame, you have to have delta t is equal to 0. So in this moving frame, so now I call it, that will be 0. So let's say this is the rest frame again. But this time I will call delta t to be 0. Delta t prime will be 0. Again, this is a very specific event. We have two events, specific event when we are going to define that our length measurement to be like that. Then we have to talk about, okay, how do we compare? Now I want to do delta z prime and z, but the easier way is to just invert it, right? Remember, I think what's the inverse of this matrix? It's just minus beta gamma. So if I multiply by the inverse, this is gamma times minus beta gamma and minus beta gamma times delta z prime times c times delta t prime, which is 0, is equal to, since it's the inverse of that quantity, that's delta z times c delta t. That's just a trick to calculate the delta z. I could have done this at this stage itself, but instead of doing some algebra, just invert the matrix. And we immediately get gamma times delta z prime, because this is 0, is delta z. Right? So I learned that gamma times delta z prime is equal to delta z. Remember, this was rest frame. This is the moving length measured in the rest frame, length measured in the moving frame. And I can then write the length measured in the moving frame is equal to length measured in the rest frame divided by the Lorentz factor gamma, but gamma is always greater than 1. So this is, so this means that delta z prime is always less than, or less than or equal to delta z. And that's length contraction. Again, if you measure it in this form, we shouldn't take every length that you see around us should not be compared this way. For example, especially the displacement of a particle, right? As you move around, that's a different length. Like this is the length of a rod we are talking about. Then, and if we measure it in this way, in the rest frame, we are allowed to measure it in whatever way you want, but in the moving frame, you have to measure the two ends at the same simultaneously. If you obey those rules, then the quantity that you measure will be contracted in that form. That's all that it means. In general, any two lengths satisfy Lorentz transformation, right? And that is a specific form. But a length measured in this, with these rules adhered to, then you have length contraction in a simple form. Okay. Any questions there? Any comments on those two before I go to the next one? Okay. The third one, which is again familiar to you guys, is what is called velocity addition. So let's say there is a frame delta z prime and c delta t prime, and it is moving with respect to the z frame with velocity v, right? So to appreciate that this matrix has only velocity dependence, right? Gamma is a function of velocity, beta is velocity. So this is like saying the moment you have an observer moving with some velocity, you will have this two quantities related in this form. So we are saying that, so there is some event happening here, so something happened, that's your zt, let's say z, comma, t, and there is a person who is moving with respect to some velocity v. He or she measures that zt to be z prime t, but there could be another observer, so this is z prime t prime. So as a zt measured by this observer as z prime. There could be another observer, let's say this is v prime, right? So there is another observer with this moving v double prime, and you say, oh, that's z double prime and t double prime. There could be many observers. So other observer also measures that, and that you say is delta z double prime c delta t double prime is equal to this one. Oh, I should say this is gamma prime now, right? So this is, let's say this is gamma 1, beta 1. Remember, beta 1 is v1 over c. So whatever is the velocity with which they are moving, that's what I'm prime is. So this is v1. That's v2. Okay. So this is gamma 2, beta 2, gamma 2. This is beta 2, gamma 2, and gamma 2. And same observation, right? Delta Z, C, delta T. I can substitute this in there. Like I can put this inside in there, or I can put this one inside in here and ask what is the connection between delta Z double prime and delta Z Q. Like Galileo would have said that if this person measures this, second person measures this, the difference in the measurement will be V1 minus V2. Right, that's what Galileo would have said. But let's see what this says. So let me invert this. This is gamma 2, beta 2, gamma 2, 2. This is the same as inverse of this, but inverse is very simple. I just have to put a negative sign in front of it. So I'd say this is gamma 1 minus beta 1 gamma 1 minus beta 1 gamma 1 and gamma 1 times delta Z prime and C delta T prime. Like between these two, what's the connection? These two observers, what is the connection? And let's call that, so that's a new variable, let's call that the relative velocity. So this will be defined to be, so we would like to find out what this velocity is. Let's say this is gamma, beta gamma times beta gamma times gamma. So I would like to equate these two and find out what is phi beta gamma and see if there is any connection. So let's expand this out. So since these vectors are out there, oops, am I within? Yes. So this is the same as saying this is gamma, beta gamma, beta gamma, gamma is equal to multiply this out. I get gamma 1, gamma 2 is 1 minus beta 1, beta 2. That's my first term in the matrix. And the second one is gamma 1, gamma 2, and beta 2 minus beta 1. Right. And next one is gamma 1, gamma 2, beta 2 minus beta 1. And this is again gamma 1, gamma 2, 1 minus beta 1, minus beta 1, beta 2. Just algebra gives me that. Equate the terms. So since it is symmetric, there are two equations in here. So I learned that gamma, if I compare them, gamma is equal to gamma 1, gamma 2, 1 minus beta. Maybe I should write the other one first. That will be like beta times gamma is equal to the off diagonal term. So that's gamma 1, gamma 2, beta 2 minus beta 1. And the other term is gamma is equal to gamma 1, gamma 2, 1 minus beta 1, beta 2. I'm interested in the velocity as measured between the two moving frames. So I do a division, right? I divide these two equations, gamma cancels out. So the relative velocity, beta, is equal to the gamma 1, gamma 2 cancels out. That's beta 2 minus beta 1 divided by 1 minus beta 1, beta 2. So if there is a Lorentz transformation connecting these kind of coordinates, the velocities will not be related by beta 2 minus beta 1. Remember, V is equal to V2 minus V1 would mean beta is equal to beta 2 minus beta 1. That's Galilean relativity. But now there is this Einsteinian relativity which comes up, which I'm sure you guys have seen it in some form or the other, at least used it in some form or the other. But it's an immediate consequence of Lorentz transformation. So now, with all this information intact and with the invariant distance in our hand, we will basically define what is for position, then define what is for velocity, then define what is for acceleration and for momentum, or actually in between we'll have for momentum, and for force. So we will be rewriting the whole of our undergraduate physics in terms of this language. But that doesn't mean that we are going to redefine velocity and all. Like when we say we are measuring velocity, we do mean that the same old velocity. Like it's only two definitions that will change and we will keep track of that. But most of the things will stay the same. It's just that we don't want to compare many things. We don't use things to compare. Like position and time are the same quantities. It's just that we don't want to compare my position with someone else's moving position. It's just we will compare the relevant terms. So we are looking for invariant quantities here. That's the one. Okay. That's what we will do. And I'll stop here. Any questions, comments? Was this reasonably clear? Yeah. Okay, good. Okay, I'll let you guys go.
Have a good one.
You too, Jeremy. Yeah.
Have a good one.
Bye, Christian. Bye, Warren.